Hello guys, and welcome to another installment of our PIC microcontrollers hardware implementation and software. We're going to be today looking at infrared. I said in my last video that I was going to be doing some infrared stuff, so playing with an infrared receiver and an infrared emitter. So what I've got for you today is we've got the schematic. We'll look, as we normally do, we'll look at the hardware first, and then we'll go into the software in a separate video. Now, what we're going to do is we're going to look at picking what infrared emitter and receiver that we're going to use for this project. I see that Radio Shack has some. However, they give you the specs on them, which is fine. They tell you what the specs are. If you kind of got to read through on their website what the specs are and whatnot. But I noticed that they're kind of pricey, so I'm going to show you guys where to, or not where so much as how you can get them at other places. Like if you've been to my channel, which I suggest if you haven't been to my channel, go ahead and go there, and if you like what you see, go ahead and push subscribe. Anyway, on my channel site, on kind of the right hand side, if you look, there's that list of a bunch of helpful links, and there's a lot of the different distributors like Newark, Mauser, Allied, you know, all those different places off to the side where you can, who actually will have these parts, and they have them for very, very, very reasonable prices. And so I suggest you kind of look there, and you get full data sheets of the part. You know exactly what part you're getting, who's the manufacturer, and everything. But for a simple, quick little project to throw together, and you got just resistors laying around, and you can purchase most of these resistors and stuff at Radio Shack. Might as well just grab them from there if that's more convenient for you. But if you're looking for, you're being price conscious, that's where you'll get the best pricing will be if you order it from one of those big distributors. Anyway, having said that, let's go ahead and look at some of the data sheets that I've got for these guys. One is, let's see, this is our emitting diode. Okay, we're going to take a look at our emitter diode first off. What this will tell you is we have a gallium acetine or arsenide, whatever, emitter. That's what we've got. That's basically the type of PN material that we're using. It is a 950 nanometer device. That tells you the wavelength of light that this emits. Now, remembering back to our back to science of our visible spectrum, let's pull that up real quick. Remember, light has a huge array. We only see a very small, as you can see by this diagram, a very small piece of it, from about 400 nanometers to about 700 nanometers is what we see actual visible light is. Once you get past 700 nanometers, you go into the infrared spectrum, which this is where we're wanting to be, because we don't want to be able to see this beam. We want it to be basically invisible to you. And so we're going to push it on up into the infrared region. Hence why we've got now a 950 nanometer light emitting diode, basically an LED. So we're up here in the infrared spectrum. We're above 700 nanometers. So now that is what we're going to look at. Now it's got all the properties of just a normal LED diode. You're going to look at like your forward current. You want to look at your forward current, see how much current you're going to have to push. Of course, this is absolute max rating, but still, how much your forward current is to push to get it to go into to get it to conduct, and that way it'll start emitting light. And you've got all your regular normal characteristics like your forward voltages, your temperature coefficients, your junction stuff, all just like a normal LED diode, except instead of this emitting yellow or green or blue or orange or purple or white or whatever, it's going to emit a 950 nanometer infrared beam that's going to come out of this. So basically the only difference between this and a normal just a normal diode that you get. Now, the part that becomes tricky is its partner, its pair, the receiving end of the deal. Now we're going to want to look at the receiving diode. So let's pull that guy up. So our receiver is, we're going to use an NPN phototransistor is what we're going to use. Which, like I said, this is basically like an optically controlled transistor. It will conduct when it sees the infrared light, and it will not conduct when it doesn't see the infrared light. So what we got to do with this guy is we have to make sure and choose one of these that's going to be able to see the spectrum that we're we're shooting for. In our case, it's 950 nanometers. So if you look down through here, there's this product summary right here. This is very helpful. It's going to tell you that you've got, basically, this thing has a viewing angle of 20 degrees, so you can be 20 degrees, you know, anywhere around it, 20 degrees away from it, you know, at an angle of 20 degrees, and it'll still pick it up. And here's what matters, is the wavelength. This can see a wavelength of 450 to 1080 nanometers is what it can see. So if you shine an infrared beam that's anywhere in that range, it's going to find it. It's going to be able to see it. Now, why is this range important? Well, depending on what type of phototransistor you choose, you can make this more narrow, or you can make it more broad, depending on what kind of signals you're going to be looking at. So if you've got, let's say we really want it to be exactly 950 nanometers. Well, this one, since it's got a pretty broad range, if, let's say, this device that we're making, whatever it may be, is going to have to play nice with other infrared devices that are in the room with it, let's say, well, we might want to, if we want to zero this in to where this is a very specific deal, let's say, we might want this to be narrower than 1080. We might want it to be only 1000 or something like that. You know, maybe even narrower to where it if anybody else, you know, basically you really got to hit 950. We might want this to be from like 800 to 1000 maybe. Is nanometers is what we want. That way it's a real narrow path that only that 950 and, you know, plus or minus a little bit it will see. So that's why that's important. For what we're doing, it's no big deal. We're going to be inside a house, no big deal playing with this. So that's probably okay. That's a good range for what we're dealing with. But keep that in mind. Keep that in mind. Application. What are you applying this to? What type of device are you going to put this in? And that's why, if you notice, TV remote controls and things like that have that kind of tinted glass that's on that. That's actually a filter. It helps filter out any ambient light, like especially sunlight. Sunlight is rough. Sunlight has all different types of wavelengths in it. It's a bunch of different things. And so that helps to screen or filter a lot of light out to where only the specific wavelength that they want to be able to recognize is allowed through. So that's why your TV remote controls and things like that type of infrared devices have that type of filtering on them. And then another thing is what this current level is this tells you your collector current that it can sink, basically, because remember, this is an NPN, so we're basically going to be pulling this down to ground. We're going to reverse conduct this is what we're going to do. We're going to basically turn the LED upside down. We'll hook power to the cathode and ground to the anode instead of the other way around. Now, what we look at is, what will this thing do in light and dark conditions? And that's where, and it's literally called that. This one is emitter collector voltage is 5 volts. Its collector to emitter voltage is 70 volts, so it can take 70 volts in the forward conduction region and 5 volts in the reverse conduction region. Also, the collector current, it can take 50 milliamps, yada yada yada. Here we go. Okay, it tells you your breakdown voltages as well as collector emitter dark current. Okay, so what this tells you, this collector emitter dark current, is how much current basically this thing leaks, because we're doing it in the reverse direction, how much current with a collector to emitter voltage of 20 volts, what it will pull. The maximum, it's either from 1 to 200 nanoamps is all it will pull. So pretty much zero. So pretty much nothing. You know, it won't pull anything. It's just almost like an open circuit, almost. You know, that's pretty small. So it's almost like an open circuit when when it doesn't see any light, when it's dark, when it doesn't see that 950 nanometers that we're going to be shining at it. Now, when you do shine at it, that's down here in this collector light current. What it will do when you slam it with, and see, this one even has wavelength of 950 nanometers. When you send it 950 nanometers, and you've got a collector emitter voltage at 5 volts, then it will do, depending on which part you choose, whether it's the B or the C, it will either do 7.5 milliamps max, somewhere around 4.5 milliamps, or 8 milliamps if you choose this one, but it can sink that much. So what you're going to do is when we size this, we're going to size resistors and stuff that will be under these be around these numbers, or you can even be lower, but it can basically sink that. So that way, that's how it. So basically, if it's dark, it's only going to pull 200 nanoamps. If it's light, it can pull up to 7.5 milliamps max. So that's what we're going to use. So that's basically the main gist of all of this. It also gives you all the timings and all that fun stuff. It even gives you a wavelength of peak sensitivity, which is 850. Range of spectral bandwidth, that's that number that we saw before. That's the total bandwidth that it sees. So anyway, so that's basically what you look for in the data sheets for these guys. Okay, so let's go ahead and go back to our circuit now. Now that we kind of have a better understanding of how these play together, what we've got is we've got a little circuit over here, and we've got a transmitter. Here's our transmitter, or our emitter, whatever you want to call it, and then we've got a receiver. This is our NPN phototransistor, and see how notice it's in the reverse conducting region, and that's because it's going to block any current while it's dark, and then when you shine the light, let's say from a transmitter, let's say we have an outside transmitter, we shine a light onto it, it will break down, so to speak, and allow current to flow through it. Okay, so in doing that, we're basically pulling. We've got a transistor here, which this is just a simple 2N7002, just a standard transistor. I think you get 300 milliamps out of this guy, something like that, 200 to 300 milliamps, something like that, maybe 200. I don't remember. Anyway, but it's just a normal transistor. We've got our resistor from gate to source to help increase the transition time of that. We're pulling it to a high, and then we're pulling the receive line off of that. See that? So the receive line is pulled high all the time until this begins conducting, and it will pull it low. Now, what pulls it low? The receiver transistor, or phototransistor. How he works is as you can see, it's being pulled high. The gate of the transistor is being pulled high. But the minute we see the light, this guy is going to allow this to conduct, which should pull this guy low and allow this to go back up. So I apologize, I said that wrong in the beginning. This guy is conducting all the time because he's pulled up to a high. So he's conducting all the time, which if he's pulled to a high, then and he's conducting, this is pulled to a low. So receive is 0 to start with initially. Then when this guy conducts, because we've shined light at him, it then pulls the gate low, forcing this to stop conducting, which allows this resistor to pull this receive line high. So kind of makes a little bit of sense, the logic of it. So when this guy, basically when you shine a light at this guy goes high. You don't shine a light at this guy goes low. Pretty simple. Same thing happens over here with transmit. Now transmit, we're going to be sourcing, we're going to have our PIC, our microcontroller, give us our transmit signal. And that's if you have both these little LEDs on the system. The transmit guy, what he does is he has voltage all the time, but he's not conducting initially. This will be 0. When this is 0, the gate voltage is 0, and he's not conducting. So this will be off. To get him to turn on, let's say we're going to transmit a pulse or something. We can pulse this line or whatever, and that will pulse this transistor, and it'll turn this guy on and off, just like an LED, just like before in some of my other videos when we made like the LED blink one, except we're using a transistor to do that, just because these take 150 milliamps. I think we saw that 150 milliamps or so of forward current. Well, our PIC micro can only source, I think, 90 milliamps of current, so we don't want to overload the PIC micro, so we're going to use a transistor to switch this guy with. And that's the reason for the 25 ohm resistor, is to then give us that close to that 150, or I think that's more like 175, I think, milliamps through that guy to ensure that he's good and on. But that's basically how we control it. We're controlling it with a transistor. So that's basically it. Like I said, you're your receive is, as you shine light at this guy, he's going to either pull this line low or let it go high, which then turns this transistor on and off, which allows us to see zeros and ones basically at this receive input. And then our output goes over here to our little transistor here. And as usual, we've got our little barrel jack into our 7805 5-volt voltage regulator that's powering everything. And we're doing this off of 5-volt logic. And that's basically it for the hardware video. Hopefully this all makes sense to you guys. But basically what I'm going to do is then we'll build something similar to this. If you built 2 of these, you could then talk between these two with just these lights, and that's kind of the plan that we're going to. I'm going to build 2 of these on a breadboard, 2 of these little systems on a breadboard, and get them to talk back and forth to each other via these little infrared guys. In fact, maybe later on I may hang another LED off of this guy, another resistor and LED off of this guy, and we'll blink LEDs on either side when commanded to, is what we'll do, and it'll be through this infrared stuff. I think that's what we'll do. I didn't put it on here, but now that I think about it, I think that's what we'll do. I'll probably edit it and put that on there, and I'll show you that. I'll edit this schematic and I'll show you that other little LED hanging off or whatever when we get into the coding video. So sorry to take a whole bunch of time, but I definitely wanted to slow down, let you guys see how to choose the emitter and the receiver, how to line them up, and some tips and tricks on light and wavelengths and all that fun stuff. So that's basically it for now. Stay tuned. I'll be uploading the code one. I don't know if I'll get to it today, but I'll upload it as soon as I possibly can. Thanks guys, keep coding and keep having fun. Take care.